Hello, everybody. I'm back. I don't know what to say. Class doesn't start for 2 minutes, so I'll just. There's a little bit of a delay with the chat. Oh, since signing in, I've lost eight viewers. That's nice. But this is our setup. It's not bad, right? Absolute crickets in the chat. Yeah, so we'll get started in about a minute. Thanks, Turner. I appreciate it. Oh, look at people like the setup. Yeah, the setup's fair, right? You know, this. I said it to my linear class. Believe it or not, probably most math professors have some sort of whiteboard set up in there. Oh, great! Nice to see you. Nice to see you, Kathy. I'm glad Andy sent you this way. Jax, welcome back to class. Lauren, thank you for the compliment. I tried pretty hard to get this set up. All right, it's 10 o'clock. So don't think I forgot. It's time for the simultaneous sip. So I know we are separated by, I don't know what we're separated, the internet? I don't know. But we can still join in together for the simultaneous sip. So let's join and then type in the word sip in the comments if you participated. That is some good coffee. Okay. Johannes, thank you for the compliment. Let's kind of recap where we were before we left for spring break and then the second spring break. Our big goal right now is to sketch graphs by hand. Okay, we want to not use a calculator or the computer to kind of understand what calculus tells us about the shape of a graph. You know, we know the derivative tells us when the function is increasing or when the function is decreasing. But there's more to a graph than that, right? And so what we're gonna start with today is checking out what the second derivative tells us about the graph, and it actually tells us quite a bit. Okay, and before we get started with that, let me just kind of announce the WebAssign deadlines. The ones that there should be nothing due tonight. So if there are, please email me and I'll update those. So everything that was supposed to be due today, I moved to next week. And then I haven't touched anything else after that. So I will continue to update the WebAssign due dates. Okay. Let's see. The test, I moved the test date. I think I emailed you about that. And then the quizzes, we'll still have quizzes on Fridays, but you'll have more time to take them. Basically, you'll have an hour to take the quiz. It's going to be the same difficulty. You'll write out your answer on a piece of paper, take a picture with your phone, and then submit it to Canvas as a PDF. There are a few apps you could use that allow you to send pictures as PDFs. I listed those in an email, so take a look at those. But if you have a favorite app, or if there's like a default app on the iPhone or whatever you use, you could use whatever makes it a PDF. Okay, something to note is there's about a 30-second delay between what I say and the comments, but I'm going to be reading I'm going to be trying to look for the questions in the comments throughout the lecture today. So if you have any questions, just ask them and I'll get to them when I see them. Okay, so we're still in section 3.3, and hopefully we'll finish that today. So we'll start with the definition. And I heard from my linear class that there were times when the pen wasn't, or the marker wasn't showing up well. Just let me know in the comments if it's that case. I have like 100 markers here I took before they locked me out of school. So some of them should work. Okay, so the definition if the graph of f, so we have a function. So if the graph of f lies above all of its tangents, then we say, and we'll draw a picture of this in a second. Then we say f is concave upwards. You may also see CCU. Okay, so we will typically abbreviate it CCU, just because it's a little easier. If f lies below all of its tangent lines, so otherwise, then we say that f is concave downwards. And the abbreviation for that would be CCD. Okay, and so just to have a sketch of what we're looking at here, what's it mean for the graph to be above its tangent lines? Well, if you look at this graph, so say it's somewhere in the first quadrant, and sketch out the tangent lines, f would lie above it. So this is concave upwards. Okay, and similarly, we have maybe a graph over here, and it's a frown face. You can check graph some tangent lines, and the graph of f is going to be always below it here. So this is concave downwards. Okay, and even just a portion of it, if I erased half of this graph, it would still be concave upward. But and so any part of this graph we'd say is concave upward. Okay. And so I kind of spoiled it. It turns out that we'll learn about the concavity through the second derivative. But before we get to that, let's take a look at an example. I know it kind of stinks that you don't have your neighbors to work with anymore, like we did in class. So I would recommend, if you have the ability to, I don't know, maybe FaceTiming one of your friends during this lecture. That could be a terrible idea. I don't know. To work together, or just work by yourself. I don't know what the best option is, but if you do like working with your neighbors during these types of examples, there's other technology you could use, Zoom or FaceTime or Skype, or just a good old-fashioned phone call could help. Okay, so the example is on which intervals is f concave up? And again, we also will use the abbreviation concave up instead of concave upwards. It doesn't really matter. And then what about concave down? Okay, so that's going to be the question. I'll sketch out the graph. Okay, so we start. I'm just going to block it, and then you can see it when it's over. Okay, and now I know that F is the letter after E. I just didn't include that letter because I named the function F. I didn't want, well, maybe it's more confusing this way, but F will represent the function here, so we just had to skip a letter for these intervals. But so now the question is, on which intervals is our function concave up? And then what intervals are they concave down? Is our function concave down? So if you want to just write in the chat, maybe what you have for some ideas, probably best to type it in interval notation. But I'll give you, let's say, 30 seconds to copy all this down and think about it, and then we could talk about it together. And I say 30 seconds because that's how long it takes for the chat to get to me. All right, nobody has any thoughts? Or you don't want to type? That's fine. That is fine. I'll give you 10 more seconds to type in some thoughts. Look at this, 32 viewers. I'm impressed. I'm glad you are all here. Akil, thank you for volunteering. Yeah, concave down, we're saying A to B, let's see, A to B, C to D, and G to H. Yeah, so you want to look at the parts of the graph that are kind of in the frown face or a part of a frown face. Right, and so clearly A to B is a frown face, so we'll add that to part of our interval, and now we'll just go one section at a time. So from B to C, it's up. It's a smiley face, so it's going to be concave up. And here we separate all these intervals with the union notation. Now let's go to the next one, C to D. Now I know it's not a full frown, it's just half of a frown, but it's still bending downwards. So that will be concave down. D to E is a full smiley face, so that's concave up. Addie, I'll address your question in a second. E to G, we have a half of a smile, so it's concave up. And then the last section is a half of a frown, so it's concave down. Unintentional rhyme. So they're open intervals. There's a point at each of these, where they switch. If my drawing was correct, the tangent line. So for instance, here at E, there's no tangent line because it's a cusp. So it doesn't make sense for the tangent line to be above or below. But at these points here, the tangent line would be above at some points and below at other points. So we would say that it has we'd say it's zero, the concavity is zero. It's not concave up or it's concave down. So yeah, so all these should be open intervals. And these points are going to be of interest to us. We're going to call them points of inflection. That should be a term that you've heard quite a bit in the news lately with the talk of the flattening the curve and stuff. They want to kind of, we're looking for moving the point of inflection. Yeah. Okay, so this is the big idea. And so it turns out that the second derivative is how we test for concavity. Okay, and so let's write that out now. So this is called the concavity test. There's two parts to it, but they're They're both pretty short. The first part says, if f double prime of x is greater than 0, then the graph of f is concave up. And you could guess what the second part would say. It says if the second derivative is negative or less than 0, then the graph of f is concave downwards. Okay, so we're going to be using the second derivative to tell us about the concavity of our graph. And so we're going to basically, the way these problems are going to work out is we're going to find intervals when our function is increasing or decreasing. We'll also find the intervals when our function is concave up and concave down. And then we'll put it all together and sketch the graph. Okay, and so let's write out one more definition before we look at another example. So the definition is a point P on a curve y equals f of x is called an inflection point if f is continuous there, and the graph of f changes concavity at this point. You look like the fake brother of Daniel Day-Lewis in There Will Be Blood. Thank you, Wiki 119. I'm not familiar with that movie, but maybe your classmates could tell you if they agree or not. I don't know. Okay, sorry. I won't get distracted by the irrelevant comments anymore. So yeah, another term instead of an inflection point, you may hear point of inflection. So the abbreviation for this is POI, points of inflection. All right, and basically where these inflection points happen or where they occur is when our second derivative is 0. Right? Think of them also as it's the same idea as a local max or a local min, but in the second derivative sense. Okay, so the example is going to be sketch a graph that satisfies a bunch of conditions. Okay, and so it's going to satisfy some conditions about function, the derivative, and the second derivative. Okay, so 1, f of 0 equals 0, f of 2 equals 3, f of 4 equals 6, and f prime of 0 equals f prime of 4 equals 0. Okay, so that's our first condition. Jax, I'll answer that in a second. Let me finish writing this down. You'll see there are, I'll answer it now. Yes, y equals x to the third. So if you look for the horizontal tangent there, it's at the origin and it's also a point of inflection. Do we get a point of inflection when y equals 0? No, it's a point of inflection when the second derivative equals 0. So y double prime. But we are going to have to check that we go from concave up, that we switch concavity. So just because the second derivative equals 0 doesn't mean we'll have a point of inflection, but it's a good candidate for where the points of inflection could be. Okay, so we have this condition. The next condition is the derivative is positive on the interval 0 to 4 and negative for the other values. And then the last condition is that the second derivative is positive when x is less than 2. Second derivative is negative when x is greater than 2. Okay, and so just a little hint before you get to writing your solution. If you take a circle and break it up into 4 quadrants, this part here, this curve, is what it looks like when you're concave down and increasing. Right? So we have a concave down function that's increasing. It would look like this. This is concave down and decreasing. I mean, they should be connected here. Here is concave up and increasing. This is concave down, concave up and decreasing. So really what we want to do, and let me get out of the spotlight there. Really what we want to do is take our information from our example here and build maybe 2 or 3 minutes to see if you could get started on this. During that time, I'll answer some questions if anybody has any questions. Yeah. I mean, I'm sure this is all kind of odd for you guys as well, but you do not understand how weird it is to be teaching to just a webcam. Like it's nice to see the eyes and the reactions and all this stuff that we had in class. We'll get used to it, but it's definitely different. It's definitely different. Okay. So this panel here will be where we kind of write our answer, where we make our sketch. Here will be where we do all the work. Okay, so basically how we're going to do this is we'll take our information. So this part is nice. Part 1 is nice because it kind of tells us, some of the important points on our graph. But 2 and 3 are really telling us all about the shape of our graph. Okay, so what we'll do is we'll take our number line, and break it up at every x value that's kind of mentioned along the way. So for instance, here we have our number line. That's going to be kind of representing our domain. And we'll break it up at 0, 2, and 4. And then what we'll do is we'll just check, is our function increasing or decreasing on each of these segments? Is our function concave up or concave down on each of these segments? Okay, so I'm going to kind of go ahead and start writing out some work. Please ask some questions if you have them. I'll get to them. But so let's just go one segment. So this is the x values that are less than 0. On that interval, our derivative is negative, so we're decreasing. And we're looking at x values that are less than 0. So in particular, they're less than 2. So our second derivative is positive, which means we're concave up. Okay, and then we could look over here at our circle, the circle of truth, and ask, what does our curve look like when we're decreasing and concave up? It looks like this segment here. So the first part of our curve will look like this. I would love for people to either say like yay or nay if they're following along in the comments, just so I can see a little bit of feedback, but it's okay if you don't. Okay, from 0 to 2. So our x values lie between, in particular, 0 to 4. So our derivative is positive, meaning we're increasing. So our x values are between 0 and 2. So in particular, they're less than 2. Our second derivative is positive, so we're concave up. And then we look at our circle, and increasing concave up means we have this as part of our segment, as part of our graph. Okay, thank you all for the responses. I appreciate it. Just because it is, just a little odd, just having silence. Okay, when our x value goes between 0 and 2, so we're looking here still, right? X values would be 0 and 2. Our derivative is positive, so we're increasing. And our second derivative is negative, so we're concave down. Increasing concave down looks like this. And then last, our x values are greater than 4. So we're decreasing and we're concave down. To plot some points. Okay, so this tells us that we have the point 0, 0 on our curve. 2, 3. So let's go over 2 up 3. And then we also just have to make sure that we have horizontal tangents at x equals 0 and x equals 4. So we'll just check that at the end. Okay. So to the left of 0, we're off in this direction. Between 0 and 2, let me really exaggerate this. They look like this. Between 2 and 4, and 4 to infinity, we look like this. Okay. Okay, and then just for the sake of completeness, I know this wasn't part of the question, but let's label some of the points of interest. And again, I know because the feedback takes too long for you to respond, maybe you could just say it out loud to your computer screen if you're alone. But this point here is a local min. This point here is a local max. And this point here, I'll give you the time to answer. What is this point? So I'll give you have time to type it in. Just type in IGK if you great. We change from concave up to concave down. And our function is continuous there. So it's a point of inflection. Good. Yeah, so this here, sure, we weren't given an explicit formula for our function, but all of this information we could put together to get the shape of our graph. Okay, so are there any questions? Let's move on then. This here, I would write in your notes, and it's going to be handy for. This will be handy for the next couple of units. Are the local mins and local maxes also points of inflection? No, they're not, because at these local mins and maxes, our concavity doesn't change. Right? It's still, we're going from concave up to concave up, or concave down to concave down. So they're not points of inflection. It's only when our concavity changes. And so something to notice, and we'll write this kind of as a result, we have a local min when our concavity is when we're concave up, and we have a local max when we're concave down. And that's always going to be the case. So this is called the second derivative test. Okay, so we start with suppose f double prime is continuous near C. Okay, so we have a second derivative that is continuous near some value C. So the second derivative test says this is a test to check if we have a local max or a local min. So it says if f prime of C equals 0, and f double prime of C is positive. So if our derivative is 0 and our second derivative is positive, that's looking like in this case, the second derivative test says we have a local min. Okay, and similarly, if our second derivative is negative, then we'll have a local max. Okay, so the second derivative we could use as a way to check if we have a local max or local min. I don't know if you would find this any easier than our previous method, which was checking if our Okay, so let's take a look at an example. Okay, so basically what we want to do in this example is we're going to find the local max, local mins, and points of inflection, and then sketch the curve of some function. So let y equal x to the fourth minus 4x to the third. We want to discuss concavity. Points of inflection, local maximum, local min. I guess that's all. And then sketch. So basically, I know this is kind of worded a little bit weird. I should have worded this differently, but basically we want to do what we did in this example, but with a function that we're actually given an explicit formula for. Okay, so I'll give let's say about a minute to just if you have any questions or if you want to share some ideas on how you get started with this question. But if not, I'm just going to kind of work it out and kind of talk about it along the way. Look at this, 30 likes on this video. This could be my most liked video since I attempted to make a viral video that I will be sending to you in a few weeks. Oh my gosh. Oh my gosh, more people are upvoting. Okay, I did not mean to just beg for the upvotes, but I appreciate it. Okay. Yeah. Basically what we want to do in these questions is we want to find the first derivative and the second derivative. And then we'll check when they're positive, when they're negative, and when they're zero. Connor, that is a great observation. Subscribers are through the roof. That's what happens when everybody moves to online is say, subscribe to my channel. Okay. Yeah, so for these types of questions, for these curve sketching questions, we're going to always start by taking the derivative, taking the second derivative, finding when they're positive, finding when they're negative, and finding when they're zero. Okay. So we'll start by just taking some derivatives. Oops. Thank you, Abigail, for suggesting what the derivative is. So y prime is equal to 4x to the third minus 12x squared. And then it's best to factor if you can. So it's 4x squared times x minus 3. And the reason why we factor is because we're going to be setting it equal to 0. Okay. And so we need the second derivative. Is 12x squared minus 24x. And again, we could factor this. To 12x times x minus 2. And so let's find when they're equal to 0. Or so, sorry, we should find the critical numbers, right? Let me get out of the shadow. I got to practice this. We want to find not just when it's equal to 0, but also when they're undefined. Okay, but these are polynomials, so they're always defined. But in general, we'll have to check both when they're 0 and undefined. Okay, so the critical numbers are x equals 0 and 3. And then we should find when the second derivative is equal to 0. Okay, and so what we'll do, again, is we're going to take our number line. We're going to take our number line and we'll break it up at the critical numbers and also I mean, these are also they're not quite critical numbers, but they're the same idea. When the second derivative is equal to 0. Okay, they're critical with a lowercase c. They're important. Yeah, Jared, you're right. The critical numbers are when f prime is equal to 0 or it doesn't exist. Okay, so we got to check both. In this case, we only have to check when it's 0 because it's a polynomial. Okay, so let's break up our interval. We'll break it up at 0, 2, and 3. And so let's kind of so this will be y prime. This is y double prime. Our test values could be -1, 1, 2.5, and 3 point, or let's just say 4. Okay, and so if we plug in -1, we get, and it's best to plug it into the factored form because it's easier to work with. If you plug in -1, you get a positive times a negative. That's a negative. And you could go through and check all these on your own if you'd like. You plug in 1, you get a positive times a negative. That's a negative. You plug in 2.5, you get a positive times a negative. That's a negative. And if you plug in, did I disconnect? I hope I didn't. If you plug in 4, well, nobody will respond if I disconnected. Okay, let me know in the chat if I disconnected. Whatever. If you plug in 4, you get a positive times a positive, which is a positive. Nobody's responding. Okay, well, I'm going to keep going, and hopefully this is recording still. Now, we do the same thing with the second. It just doesn't work anymore. If you're connected. If you're here, great. I'm not sure if we lost everything. So I'm going to finish this problem, and then we'll quit. All right, so we're decreasing and concave up. So decreasing, concave up, looks like this. Decreasing, concave down. Decreasing, concave up. And increasing, concave up. Okay, and what we should do is figure out what are these points. Okay, well, it seems like people are still here, so maybe the chat just broke or something. We have the point 2, comma, 16 minus 32 is -16. And x equals 3. We get 3. 81 minus 4 times 27 is -27. Okay, so it's not drawn to scale, but it gets the general point across. Okay, I just got a text saying that it's working but glitchy. We'll try to fix this, but okay, so the general idea is we just connect all the dots, and we should label the interesting ones. So here, 0, we went from concave up to concave down. That's a point of inflection. And then here at x equals 2, we went from concave down to concave up. So it's also a point of inflection. And we have a local min down here. Okay, well, it kind of ended a little rough because of technology issues. If you're still here, let me write out one more example that you should try tonight. And we can start with it tomorrow. So do the same problem, but with y equals x to the 1/3 times x plus 4. Okay,